Okay, so good afternoon. Hello everybody. It's my pleasure to start our second seminar today. Or just now, concerning quasi-periodic oscillations, neutron-star, low mass X-ray binaries. And the seminar will be given by Dr. Javlon Rayimbaev, our dear guest from Uzbekistan, from Tashkent. And I hope you all will enjoy the seminar. Thank you.
Thank you. Thank you in introducing. So I will talk about the physical mechanisms of this quasi-periodic oscillations observed in the low mass X-ray binaries sourced by neutron stars. So, and some explanations of the oscillation mechanisms. And actually, X-ray binaries, the binary system, which consists of some neutron star or black hole and some companion in optical companion, which is seen in the optical band of electromagnetic wave, and then this second companion is invisible in optical band, so we can observe them in X-ray band of electromagnetic field. So the mass of companion star can be different, and according to their mass, there are three types of binary systems: X-ray binary systems, high mass binary systems, and the intermediate mass binary systems, and the low mass X-ray binary systems. So we are interested in this low mass X-ray binary systems, which are mass of the this companion star is less or equal to the one solar mass. And the X-ray in this accretion disk around the central object is about the 10 in power 63 to 10 to the power 68 ergs per second. And the characteristic ages of this system, actually this system, we understand this system is central object. Actually, the main characteristic of ages of neutron stars, for example, are 10 in power 10 years, and the magnetic field is weak enough in low mass X-ray binaries. Is about 10 in power say 8 and 10 in power 9 Gausses. Actually, neutron stars we can observe as a pulsars with magnetic field about 10 in power 8, 10 in power 11 or 12 or more, and their magnetic field is 10 in power 15 around. We can observe them as a magnetar, not companion of not as the binary system. In the from optical to X-ray band of electromagnetic field as a pulsar. So actually, this luminosity of accretion disk, we see this 10 in power 16, and we so to 6, and we will compare it this Eddington mass luminosity. And what is the physics of Eddington mass or Eddington luminosity? This is some limit for mass or luminosity which can ordinary star or accretion disk can radiate. So the calculation is quite simple. We use the balance of between the forces, radiation and the gravitational force. So we have some sphere assume. So in this inside the sphere radiation full, and the radiation pressure is makes the medium outside, and the gravitational makes it inside. So compress it, and here the balance of between the gravitational force and the radiation force. This is a FR corresponding to the matter distribution, and here the K opacity, which is proportional to the Thomson scattering of photons with the electrons in the medium or protons. And if this matter of the star or accretion disk is homogeneous, this is a spherical, we consider it's a spherical symmetrical star. This is equal to the 4 pi r square, and from here we can extract this. If we put the 4 pi r square here, and this is the mass of protons, and this one is the Thomson scattering cross section, and we can get it is from table, and it is it is the constant, and we can calculate as Eddington luminosity this as a 1.3 10 in power 38 arc per seconds, and with the normalized mass of the star. So if it is less than 1 solar mass, it will be this quite higher than this. So it is Eddington luminosity of the star for the stars are depend on their mass. And how to extract from here mass ratio. So as the star radiate, the star loses its mass as for converting to the electromagnetic radiation. So mc square gives us mass energy of rest mass, and as star radiate radiation, so mass energy rest mass converts to the electromagnetic luminosity. This is efficiency of energy efficiency. So it is for example, it is for star with thermosynthesis reaction, it is 1/100. So it is about 1%. So it is for the accretion disk in the Hartle-Thorne model, it is about 10%. It is the 10 to 100 times larger than the solar efficiency. So from here we can extract this Eddington mass ratio. So Eddington mass rate. So accretion disk. If we consider accretion disk, so accretion disk flows into the star, and during the accreting matter flow, the accretion disk radiates. So here I will talk about the QPO sources in the Z and the atoll QPOs from the Z and the atoll sources. Z sources, atoll sources, we know this hard soft color diagram, and this sources observed in this soft diagram. Actually, it is intensity. Hard color is a frequency. And from here, we show if the data, observational data, give us Z shape, and if the Z sources and atoll shape, this is atoll islands shape. We know this is atoll. So we call this atoll sources, and actually in atoll sources, mass rate of accretion disk is from 0.01 to 0.1 Eddington limit, and then in this Z sources it is quite quite higher. It is from 0.1 up to the 1 Eddington limit. And the magnetic field in the atoll sources around this 10, about 10 in power 8, and in this Z sources 10 in power 9. So in the logarithmic dependence of logarithmic values of magnetic field and mass rate, we see that this Z sources lies on the top at the on the top with the higher magnetic field and the higher values of mass rate. So here are some categories of quasi-periodic oscillations in neutron-star low mass X-ray binaries, and here we see that this low frequency QPOs, and here these categories are high frequency QPOs, and so we show that at the hectahertz QPOs and kilohertz QPOs, and the low frequency QPOs has 3 categories, and in turn, so it is which is horizontal branch oscillations and normal branch oscillations and flaring branch oscillations of accretion disk. So it corresponding to in this from 5 up to 7 it is normal branch oscillations, and from 7 up to 20 and it is for FBOs, so for flaring branch oscillations, and from 15 to 55 it is horizontal branch oscillations, and hectahertz is from 100 up to 200. Actually, these oscillations are seen in mostly from millisecond pulsars, which has rotational period from 1 millisecond to the 10 millisecond pulse neutron stars. And kilohertz, it is observed in these are observed as a twin peak QPOs, and sometimes instead twin peak we observed in one peak, for example in Scorpius X1 and 4EU 1920 and this frequencies moves up and up down in this frequency range from 200 to 1300 hertz, and in kilohertz oscillations, in this mass rate falling to the central neutron star is quite lower than this, and here some correlations between the upper and lower frequencies in the twin peak QPOs, and some offsets has been classified as a lower frequency in this power law and the linearly dependence of twin peak QPOs, this upper and the lower frequency. Here the B and the AB parameters are corresponding to the frequency value is observed from this low mass X-ray binaries. And here I show some example for the low frequency QPOs and the hectahertz and the high frequency so kilohertz frequency QPOs. Actually, as I told, so twin peak QPOs has the upper frequency and the lower frequency. So most of observed twin peak QPOs have been observed in the neutron star low mass X-ray binaries, most of them, this black hole candidate is in the low mass X-ray binaries. There are 4, and these 4 are has the same rate about this actually. Mean values of this upper and lower frequency rates is about 3/2, and here for example in GX51 or Scorpion's X1 object has several data. So this several data observed in several in different time scales. For example, we observe some this point in some period, and after that we in this band this twin peak QPO disappears and shown in other bands, and this is a full picture of all observations. So from this point of view, this mechanisms of quasi-periodic oscillations from neutron-star sources are quite difficult than this complex than this black hole sources, and this ratio distribution. We can see this observed ratios. This ratio, I mean this upper and lower frequency ratio here, and the number of observed QPOs in this ratio. In this ratio, for example, 5/4. We about 6, and in this 3/2 about 8 peaks are observed. This frequency are observed in neutron-star sources. And now we will go step by step theoretical explanations of QPO mechanisms, and using this neutron-star parameters, and the orbital motion of particles around the neutron-star. This orbital frequencies of around neutron-star is about 1,200 hertz. Here the mass is taken as 1.4 solar mass, and the inner edge of the accretion disk is about 15 kilometer, and the observations kilohertz QPOs in this range we may, as I told about, and this estimation show that this kilohertz QPOs should be explained, or upper frequency of kilohertz twin peak kilohertz QPOs can be explained as a orbital frequency of particles of the inner edge of the accretion disk. Here the interpretation of kilohertz QPOs can be generally described by the two constants. So the interaction between magnetosphere and the accretion disk flow at the inner boundary of the accretion disk, and the relativistic effects of particles in the inner edge of inner boundary of accretion disk, and such as this frame dragging effects. Since the neutron stars are rotating object, and the different oscillation modes of plasma in accretion disk. So let's first, it is magnetospheric bit frequency mechanism. In this mechanism actually explains this horizontal branch oscillations, normal branch oscillations, and kilohertz twin peak quasi-periodic oscillations. So this model predicts the universal relation between this high frequency horizontal branch oscillations and the neutron-star spin and the upper frequency QPOs. This model can explain this neutron-star in the neutron-star magnetic field about this 10 in power 9 and 10 in about 10 in power 9 and 10 in power 10 when the spin and the magnetic field equilibrium. And the model requires a small fraction of accretion disk gas does not couple off strongly to the neutron-star magnetic field at the distance about 3 or 4 radius of radius distance, and now sonic point bit frequency model as the accretion disk flows into the central object, so it's this velocity increases the velocity of accreting matter increases, and when the falling velocity of accretion disk material reaches the sound speed in this medium, here the radiation will occur, QPO radiation will occur. Here this sonic radius is at some point, and this sound speed in this medium is depend on the density of plasma and the distribution of plasma actually, and this model say that this upper frequency of twin peak QPOs corresponding to the this Keplerian frequency at the supersonic point. So in this distance from the center of the neutron star and up to the supersonic radius, and the lower frequency should explain as a difference between this Keplerian frequency at the sonic point and the neutron star spin. And it shows that this neutron star, this difference between upper and lower, so lower peaks should be equal to this neutron star spin. And here, as an example, it is shown this the second second frequency and the difference of between this two peaks, and the ratio is shown for the Scorpios X1, and here this mass is 1.59, and the sonic frequency of at the sonic frequency of particles at the sonic radius is about 352, and this is a theoretical model, and here the observational data, and we can see how this fits with the model fits with the observation of data. Actually, this amplitude of peaks depend on the neutron star's magnetic field at the surface of the star, and the accretion disk according to this model can undetectable sometimes, and Neutron star's spin interacts with the orbital motion of accretion gas and at the sonic radius with the frequency equivalent to the sonic point bit frequency. And this mode model, in this model, one of the peak should be actually in most models of quasi-periodic oscillations in neutron stars explain its upper frequency of twin peak QPOs from neutron star can be described by the Keplerian orbital frequency at the sum radius. Its sum radius, it depends on two different QPO models, and during the accretion process, some part of accretion disk mass with the large moment of large angular moment forms the Keplerian disk, and while another part undergoes, and the transition of accretion matter from the Keplerian to sub-Keplerian flow occurs when the centrifugal force slightly exceeds the gravitational force. So in the stable circular orbit around the neutron star, the particles via this centrifugal and the gravitational forces are has some equilibrium limit, taking account the Lorentz force and the angular momentum of these particles, and when this equilibrium has breaks, some kicks or shocks from supersonic regime of accretion flow occurs, which also responsible for the super Keplerian frequency. So here we know this accretion disk consists of charged accretion disk of neutron stars consists of charged particles, actually fully charged particles, and this accretion disk has a high accretion rate, and the temperature of the neutron star accretion disk high enough is due to the fraction in the accretion disk and oscillations some in accretion disk, and it depends on this some modus in accretion disk oscillations, and this idea is similar to the coronal oscillations in solar physics, where magnetic hydrodynamics turbulence derived by the Alfven wave oscillations occurs in the magnetosphere of the sun coronal atmosphere. We can see here some types of these are actually some magnetic field tubes, and where charged particles always follow this magnetic field lines due to the strongest of the magnetic field, and during the rotation of neutron star, this magnetic field curve creates this parallel electric field high enough. This parallel electric field forces to the charged particles follow to along the magnetic field lines. So this Alfven wave oscillations frequency can be is dependent on the magnetic field. Actually, in this according to this model, So particles from accretion disk flows into the polar cap of the star, not only directly at the equatorial plane of the star, but following this magnetic field lines, they falls into the polar cap. And here this free fall velocity and this estimation also this Alfven velocity also it is about kilohertz for the neutron star with the magnetic field value. I forgot to show some estimation calculations for the magnetic field value 10 in power 9 Gausses. Now it is relativistic effects in the accretion disk. So relativistic precession model, it is a very simple model. We show this precession in our actually this in the stable circular orbitals, particles should follow this circle shape orbit, but when have some displacement from the minima of effective potential of particles, this displacement makes the oscillate the particles in radial direction, and we can see this in this form of relativistic precession of particles. Here this Lense-Thering precession, which is can be calculated as orbital frequencies, and this E is angular momentum of the star. This for the star, it is about typical neutron stars. It is about typical means mass of the star is 2 kilometers. So it is 1.4 times larger than solar mass, and the radius of the star is about 10 kilometers. And we calculate this. We may calculate this. We may estimate this. Inertial momentum of the star is as a star is as the shape of sphere, and we can get this relation. But in realistic case, this inertial momentum of the sphere is depend on equation of state, because equation of state makes the radius changes the mass of the star and the radius of the star. It is there are more than 100 equation of state has been studied by several authors, and we can get some measurements. We can get some limits for inertial momentum of neutron star, and using this relation, we can get some relation between this quasi-periodic oscillations and the equation of nuclear model in the neutron star, interior of the neutron star. So precession frequency actually as is a classical precession part, consists of two parts, Lense-Thering part and the classical precession part. And according to this relativistic precession model, upper limit is always this Keplerian frequency, and the lower frequency of the twin peak QPOs is the difference between the Keplerian and the radial oscillations. So since this is a view of in the constant plane. Here we can see that in even this central object, in this case it is the black hole is shown. So in the central objects, if it is rotating, this the plane cannot be constant, and the position of the equatorial plane changes depending on the spin of central object. So here some resonance cases, as we told in the beginning of the slides. Here some correlations between the upper and the lower frequencies as in this form. So here this m and n are some integers. For example, we see that it is 3 or 2 or 4 or 5 or 3, 4 or 3 for twin peak QPOs observed in neutron stars. And the relativistic resonance model, it is for the first time, it is proposed to explain the discovery of 450 Hz frequency from black hole candidate G0. This object J16, 55, and 40. It is a single peak. Sometimes, and sometimes it has in kilohertz band two double peak with near this and with the frequency ratio 3/2, and but this frequency has no lower frequency due to some reason. It is unknown why there is no lower frequency, and the dynamical origin of high frequency kilohertz QPOs in both neutron star black hole candidates and in neutron star candidate sources and neutron star sources are the same in this model, relativistic resonance model, but with the different frequencies. The frequency differences in black hole and neutron star candidates are depend on with the magnetic field values, magnetic fields of neutron star. But we know this in magnetic field around black holes are weak enough, and neutron star it's quite higher. This in relativistic resonance model has also similar effects between this similar mathematical correlation between upper and lower frequencies, and the orbital frequency and the elliptic frequency of accreting plasma have simple ratio in this form. Actually, this oscillations of in the accretion disk has horizontal oscillations, which is dominated by the vertical oscillations, is caused by this P modus and J modus. P modus is resulting this pressure of variation of pressure of accretion disk. And G modus comes the variation of gravitational field in the inner edge of the accretion disk. So rotation of effects of neutron stars here. So we know this neutron stars are rotating objects. The rotating objects, so as neutron star rotates, so we consider this neutron star magnetic field is the dipolar. This dipolar rotation creates induced electric field. And here the complex forces acting on particles, here the gravitational rotational gravity electric magnetic creates the Larmor frequencies. So the Larmor frequencies is proportional to the angular velocity of neutron-star, which is leading to split the vertical direction of the disk. And the rotation of neutron-star breaks this. If you consider this, breaks this spherical symmetry, and it produces space-time this axial symmetry. As a result, the plasma obtains the local angular velocity in radial velocity, and this radial velocity is proportional to the square of neutron-star angular velocity. It is quite strongly depend on this neutron-star rotation, and it also has some correlations between the radial and the Larmor frequencies, and in this form, and we can also construct this correlation using these integers. And the radius of closure orbitals around neutron stars can be found using these these expressions, and putting here we can extract this expression as the radius of inner edge of the accretion disk in neutron stars. So this also inversely proportional to the neutron star angular velocity, and it is proportional to the mass of the star. And the rotation here, as we mentioned about that the circular orbits of the accreting matter in a stable orbitals, and the plasma moves at Keplerian velocity and radiates X-ray, where the angular velocity of the first derivative of angular velocity of particles equal or larger than 0, or second derivative of effective potential of these particles equal larger than 0, and where the effective potential take minimum, and the slightly perturbation of particles causes to particle oscillations around the minima of effective potential. And if this perturbation high enough to oscillate the particles around the minima, this particle leaves this stable orbitals, and the plasma follow the helical track in spiral. So this is due to the magnetic field, and this helical spheral radius and the frequency of this spiral orbitals is depend on the magnetic field. It's the Larmor frequency, and this causes to some dissipative processes in accretion disk of neutron stars due to the viscosity and the collision of elements and the shock waves in the neutron star accretion disk. This is a short review for the QPO mechanisms around neutron stars. So thank you.